Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to solve walk a matrix. This prompt states you're given a 2D array or a matrix, and you want to return a 1D array containing all this matrix's items inserted in clockwise order. You start walking around the outside in a clockwise fashion, and you work your way inward, forming this kind of spiral until you reach the final item in the middle. So what we'll see is there aren't really any traps or tricks to solving this question. It's all about understanding this complex data structure, how to walk through it, and then translate your logic to code. It's actually a common interview question, and one I've seen myself a few times. So we start our clockwise walk at the point 0, 0 at the top left. We add the result 0 to our output array, and now we want to walk right across this first row through all the columns. So we go from 0, 0 to 0, 3 and add 0, 1, 2, 3 to our results. We hit the edge. To continue our clockwise walk, we need to go down. So we go down this final column from 0, 3 to 3, 3 until we hit the next edge. So we add 3, 4, 5, 6. To continue our clockwise walk, we need to go left. So we go from 3, 3 to 3, 0 back across this final row from the final column to the first column. So we add 6, 7, 8, 9, find another edge, and now we go up. So we go from 3, 0 to 1, 0, and notice we stop before 0, 0 because we've already added that item to our results. So we add 9, 10, 11, then we go right, but then again we stop before we reach an item we've already seen. So we go from 1, 0 to 1, 2, we add 11, 12, 13, then go down, find another item we've seen, so we go back left. We reach the point 2, 1, which is the result 15, and our final item. So now let's view this as paths. We went right, down, left, up, so we walked this entire outer perimeter. Then we go right, down, left again, and we found our final item. So we can already see we're having some repetition in the logic, and more specifically, we have one full walk, and then we move that walk inward. And it's also worth noting, our matrix can be a vertical rectangle, a horizontal rectangle, or even a single row or column. It doesn't have to be this perfect square, but that's what we'll use in our breakdown, and we just want to make sure our logic will apply generally. So after walking through it, we realized there's probably 3 questions that we need to answer. 1, we saw that we always want to stop and not count the same node multiple times. So how do we view a node as already being seen? The first thought might be that we can add a data structure, like a hash table, and that's usually a good thought because we get these constant time, lookups, and inserts, but we'll think through that and see if there's an even better method we can use. The next is how do we walk this matrix code? How do we go around these edges and make sure we're always turning inward each time? And finally, we saw that we returned after adding that last item. How did we know we found that final node in our matrix? So we saw when we viewed the paths that our problem repeats. We went right, down, left, up, and then we just followed the same logic again. We moved inward and went right, down, left again. So instead of necessarily viewing this as spiraling, we can actually see it as walking a perimeter, touching all those items, and then moving this perimeter inward. So it's this constant right, down, left, up walk at varying perimeter sizes. Specifically, we saw when we reached 1, 0, we moved our row in by 1 spot. So instead of going across the 0 row, we went across the 1 row, so plus 1. And then we moved right, and then we ended 1 column back in. So instead of ending at the 1, 3 column, we ended at the 1, 2 column and walked down that. So we can see what's happening is we're tightening our bounds by 1 index each time when we finish either a row or column, moving right or left, up or down. And this applies to a perimeter of any size. We would walk an outer perimeter, remove that, walk an outer perimeter again, and remove that. So it's just this shrinking repeated logic of walking the same perimeter each time and then bringing our indexes inward. So now let's see how we actually traverse each side. And we can do this using for loops, or specifically 4 different for loops, one for each side. One for the top, right, bottom, and left. For the top, we keep our row fixed at 0, and then we start a for loop and go from 0 to 3 at the columns. Then for the right side, we fix our column at 3 and then increment up the rows. So start our for loop at 0, 1, 2, 3. Then for the last row, we fix it to 3 and increment backwards down our columns. So 3, 2, 1, 0. And then finally, with our last for loop, we fix the column at 0. We start our for loop at 3 and then increment backwards to 1. 3, 2, 1. So everything is just based around knowing that starting and ending column or row and knowing which one to keep fixed. So if we translate this to code, to walk the top row, we start at the 0 column and end at the last column, or the column length minus 1. So in each iteration, we keep our row fixed and then just change that column value. Then we walk down the right column. This time we keep our column fixed at the final spot, start our row at 0, and go through the length of the rows. To walk the bottom, now we start working backwards. So we start at the final column and then work down to 0. So we go column minus minus each time, and we keep our row fixed at the final row. And then finally, to walk up the left column, we keep our column fixed at the first column and start at the last row and then work backwards. However, this time, we want to end at 1 instead of 0 because we've already used the 0 value. So that works for the outer perimeter, but how do we account for all the perimeters? When we move inward, we want to use different indexes for iterating across, down, left, and up. Well, when we iterated across the first row, we kept this 0 index fixed. That means there should be no more items within this row that ever need to be touched. So if we use a variable to track this index, after we finish that row, we can do ++ to move it inwards. And then this will get us to our next starting row and allow us to end before reaching that row on the final loop. The same is for the final column. Once we use that, we want to move it inwards 1, but this time -1. So now our final column is 2 instead of 3. The same can then be said for the bottom row. We move our row up 1 or -1 from 3 to 2. And then finally, for the first column, after we use it, we move right 1. So what we do is after we use either a full row or a full column, we can move its index inwards, so then we never touch that row or column again, and use those for our starting and ending bounds of our for loops. And now we introduce 4 new variables: start row, end row, start column, end column. And these will dynamically track the bounds of our perimeter, so we can move it inward each time we use an entire row or an entire column. So when we iterate across the top, we keep our start row fixed, and we start at the start column, and then end at the end column. Then, once we use this row, we do start row ++. So we move it inward. Now we're on the last column. We keep the end column fixed, we start at the start row and end at the end row, and go through the entire side. Once we finish the right side, we move end column in by calling -, and now we have a new right bound. Then for the bottom, we keep end row fixed, we start at the end column, and do column -, and go backwards towards the start column. Once we use this row, we do end row -. And finally, we're on the left side. We keep the start column fixed, we start at end row, and end at start row, but now start row has already been incremented in, so it equals 1. So we'll end at 1, 0, because we've been dynamically tracking our bounds. So once we finish that side, we do start column ++, and then after completing this outer perimeter, we've already moved each of our bounds in one spot, and then we can just simply start again and begin the same process again. So now we're dynamically tracking our perimeter and moving it inward each time we complete a side, but how do we actually know we're done? How do we know we reached this last item? Let's very carefully track our indexes and see what's happening. So our start and end row is 0 and 3, and then the start and end column are also 0 and 3. We go across the top from left to right and increment our start row by 1. Then we go down the right side and decrement the end column by 2. Then we go across the bottom right to left and decrement our end row to 2. And finally, we complete the first loop, that first outer perimeter. We go up the left side and increment our start column to 1. Now, after we complete the first loop, our start row is at 1, our end row is at 2, start column 1, end column 2. Then we go left to right and increment our row to 2. We go top to bottom and decrement end column to 1. And then we go right to left and decrement our end row. And then we're done. So why don't we go back up this left side? That's because our start row is now larger than the end row. So we've broken the bounds, we've converged, and there are no more items to iterate through. This would also be the same for the start and end column if our matrix had a different shape. So how do we know we're finished? As long as our bounds haven't converged. Both our end row and end column are greater than or equal to the start row and start column. But also because we traverse our sides and increment, we need to add if statements within our code before we start a new for loop to make sure the bounds haven't broken before getting to that spot. And that's our logic. We're tracking the starting and ending rows and columns to create this dynamic perimeter on our matrix. This allows us to iterate around clockwise and then spiral inward as we complete a side. When we do complete a side, we simply move the bound associated with it in by 1. We just repeat the same traversal around the perimeter until we reach the center. We know we finished when either the end row is smaller than the start row or the end column is smaller than the start column. The complexity of our solution is linear time and constant space. We iterate through all n items and don't add any new additional data structures. And now we're ready to implement our solution function walk matrix. We start by initializing the results array, and now we'll initialize our variables to track the perimeter indexes. And now we can begin iterating through the matrix. We do this in a while loop. And so we iterate as long as our end row and our end column are greater than the start row and start column. Then we can begin iterating across the sides using our for loops. We iterate from the start column to the end column across the first row. So we keep the start row fixed and increment the column by 1 each time, and then we push this item to our results array. This completes our top row. So we need to increment our start row by 1. Now we'll just do the right side. We're going to keep the column fixed and iterate from the start row to the end row. So for each row in the end column, we push that item to our results. And then, since we've completed the right side, we bring our end column in by 1. And now we're ready to iterate back across the last row, going from right to left. However, we also need to check that our end row hasn't gotten smaller than the starting row. Since we've already incremented our start row after the first for loop, it's possible we are now out of bounds. If we're not out of bounds, then we do our next for loop. Since we're iterating from right to left, we do column minus minus, and we start at the end call and finish at the start column. And then again, we push each item to our results, and we keep the end row fixed while we iterate the column backwards. And now this completes 3 of our 4 sides. Finally, we need to iterate upwards to get back to our starting position. Since we're iterating up a column, but we've already decremented the end column, we need to just check that we're still in bounds. If we are in bounds, we just go through our final for loop and iterate up the left side. We iterate up the starting column. We do row minus minus since we're going backwards. We keep our starting column fixed, iterate backwards through the rows, and just push each item to our results. And then finally, we return results. We also need to make sure we decrement our end row and increment our start column after we finish the final 2 loops. So end row minus minus to account for walking across the bottom, so we bring that in. And then start column plus plus to account for walking up the left side. We run our code and our tests pass. So what we did was create a perimeter, walk around each side, and bring that side's bounds inward. This is a great question to really understand matrix iteration and feel confident with the indexing and how to iterate through them. Matrices can be common in interviews, so you want to go in confident, knowing how to approach it from the beginning. Thanks everyone, and I'll see you in the next lesson.